This is the magnetic field section of the Spiral Physics textbook. You will hopefully notice in this section many similarities to the electric field. If you turn to page 3 of the magnetic field, we read, "A different field is created when charged particles move." This is the magnetic field. So in this section, we're looking at the magnetic field, which is created from charged particles moving, and the charged particles that are moving in the cases that we are going to study are moving in a wire, and that would be a current. If you turn to page 4, we have two equations which we are going to be using to calculate the magnetic field, and there's actually a third equation as well. This equation is only for long straight current carrying wires, and you can think of this equation as being similar to when we calculated the electric field from point charges. If the wire is not a long straight current carrying wire, then we have a more general equation. This is called the Biot-Savart law, and this equation we integrate. This equation can be used in any situation, even if the wire is long straight and carrying current. So this is a more general equation, and this one will probably remind you of the equation that we had for a continuous charge distribution. Then there's a third equation, which is similar to Gauss's law. We are going to look at the Biot-Savart law first because you have that coming up in lab this week. One thing though that I want to draw your attention to for the equation from a long straight current carrying wire, instead of R hat, which is what we have in the Biot-Savart law and what we used in the electric field, we have T hat. T hat is a unit vector that is tangent, thus the T, to a circle which is centered on the source current and located at the point of interest. So the vector is located at the point of interest, and it's tangent to a circle, and the center of the circle is where the source current is. To determine the sense of T hat, place your thumb in the direction of the current flow, and the sense in which the fingers of your right hand curl is the sense of T hat. For example, if the current is flowing out of the page, we put our thumb going out of the page and the fingers of our right hand curl in the counterclockwise direction, so the magnetic field is pointing in the counterclockwise direction. And on page 5, they give us an example of how this works. So positive current is going out of the page, negative current is going into the page. If I'm looking at the direction of the field from the current which is carrying wire out of the page, I stick my thumb pointing out of the page and my fingers curl around in this direction. So you have a magnetic field. You can draw the direction anywhere on this circle, but at this specific point, the arrow for the direction of the magnetic field is tangent to the circle and pointing in the counterclockwise direction. So that gives us the direction of the magnetic field at that point. But anywhere on the circle, the direction is tangent to the circle, and for the wire carrying current out of the page, it's pointing in the counterclockwise direction. So now we're going to turn to page 16 and see how this works in an example problem. So this is our first example problem from the magnetic field section. We want to determine the direction of the net magnetic field at each of the indicated points. The wires are long, they are perpendicular to the page, and carrying current either out of the page, which is positive, or into the page, which is negative. So we have a wire which is coming out of the page, or you could say going into the page here and here. So the current's coming out of the page, going into the page. These wires are long and parallel to each other and perpendicular to the page. They look like point charges when you look at them, but they're actually wires which are coming out of the page. And we can calculate the net electric field similarly to how we calculated the net electric field. And we're going to look at the electric field from each individual wire and then find the net electric field. The difference, though, is that here the direction is given by a vector which is tangent to a circle whose center is where the source current is. So let's start off with part A, and let's look first at this point in the center here. So I will draw a circle. This is going to be a blue wire here. If I draw a circle whose center is where this wire is at this point that would look like this. That's just part of the circle. And I have to draw a vector which is tangent to the circle, which would either be pointing straight up or it would be pointing straight down. To figure out whether it's pointing straight up or straight down, I stick my thumb pointing on the page, look at the direction that my fingers are going in, so they are going in the counterclockwise direction. So over here, they would be pointing up. It might help if here we look at the full circle, just for this one case. And if I draw the direction at different points on the circle, it's always pointing in the counterclockwise direction and always tangent to the circle. So at different points on the circle, this is the direction of the magnetic field just from this wire. From the other wire, which I'm going to make black, let's draw another circle. And the current's going into the page, so I stick my thumb into the page, and the fingers of my right hand are going now in the clockwise direction. So pointing up here also, over here like this, always tangent to the circle and always going in the clockwise direction, since here the current is going into the page, so that's like this. So the net field at this point is definitely pointing upwards because the arrows from both individual wires are pointing upwards. Okay, now let's look at this point over here. From the wire which is carrying current into the page, the field is going downwards. From this wire, which is carrying current out of the page, the field is going upwards. So we have the field going up like this. Now, in order to determine the net magnetic field, I actually have to know something from the equation on page 4. So here, the field is equal to mu naught times I divided by 2 pi r. Mu naught is a constant. It is the permeability of free space. This constant is equal to 1.26 times 10 to the negative 6 Teslas times meters per amps, where amps are the units for current and Teslas are the unit for the magnetic field. And this constant is actually exactly equal to 4 pi times 10 to the negative 7th. So if you prefer using that, you can, and this is exact. I is the current, so the magnetic field is proportional to I and inversely proportional to R, which is the distance between the source current and the point of interest. Again, this should remind you of what we saw for the electric field from a point charge. For the point charge, the electric field was proportional to Q, so here it's proportional to the current, instead of being proportional to the charge. And for the electric field, it was inversely proportional to R squared, but here it's inversely proportional to R. Well, all we really need to know for this problem, since the two currents have the same magnitude, is that if we're farther away from this current, the electric field, or the magnetic field, is going to have a smaller magnitude. So overall, the net field is pointing downward, just like it would have been if these were point charges instead of being current-carrying wires, except that here in the denominator we just have R instead of R squared, but this magnetic field from the wire which is carrying current out of the page is still smaller than the magnetic field from the wire which is carrying current into the page. Okay, so over here we would have from this wire the magnetic field is pointing downwards. So everywhere to the left of this wire, the magnetic field is pointing downwards, because over here it's always, the direction is always tangent to the circle, which is pointing straight downward anywhere on this line here. And as we get farther away, the field gets smaller. Here, the wire is carrying current into the page, so I stick my thumb into the page. My fingers over here are pointing straight upwards. I'm farther away from this wire than I am from the other wire, so the net field is pointing down. If I am directly beneath this wire, the magnetic field is pointing to the right. So here we have the magnetic field pointing to the right. From the wire which is carrying current out of the page. For the wire which is carrying current into the page, if we're over here, just like we were at this point on the circle, the current, the magnetic field is going in this direction. So if we add those two vectors together, we get something like that. By symmetry, we could say this point here would have a magnetic field pointing that way. If we're directly beneath this wire, the magnetic field from this wire is going this way, just like it was at this point here. If we put our thumb into the page, the fingers are going this way. And if we have our thumb pointing out of the page, our fingers are going like this over here. You can look at this point on the circle. The magnetic field is going this way. Over here, still, it's kind of hard to, going that way. So that gives us this for the net magnetic field. And then, if we look at this point up here, from the wire on the left, my fingers are going this way. From the wire on the right, put your thumb into the page, and over here, your fingers are going this way. Remember, these vectors are supposed to be tangent to a circle whose center is where the wire is. So that gives us something going straight upwards. So here, between the two, the net field is going straight upwards. Here, the net field is going straight upwards. And down here, tangent would be pointing this way. And here, tangent would be pointing this way. Tangent would also be perpendicular to the r hat vector. So if you draw a line like this, going from the wire to the point of interest, this is blue here, then the tangent vector has to be perpendicular to that. That leaves you with two directions. It could either be pointing this way or this way, and then you can use your right hand to figure that out. So the net field is going upward. So anywhere on this line here, the net field would be going up. Okay, now for part B, we have two wires which are carrying current into the page. So the direction for the wire on the left is going to be opposite what it was in the previous problem. So now carrying current into the page, that would be going up everywhere directly to the left, everywhere directly to the right, the field's going that way, down. And let's look at other locations that we have here. So we draw a line like this. The vectors have to be perpendicular to this line. Put your thumb going into the page, and perpendicular would be going this way. I'm not taking the size into consideration now, but I'll do that later. So put your thumb going into the page, and your fingers are going like that at this point. And over here, put your thumb going into the page, and your fingers are going like this. So perpendicular to this line here and going in the clockwise direction. Okay, same thing for this wire as we had over here, perpendicular to a circle whose center is the location of this wire and going in the clockwise direction. So clockwise here is down, here clockwise is up. Here I'm directly between the two wires, so these should have the same magnitude, and the field here would be 0. And over here, the field is pointing upwards. So these two add together, and these two add together. And then directly beneath, clockwise would be that way. This vector is longer because I'm closer to this charge. If I add those two together, I get something pointing like this. You can compare that to what we had over there. Clockwise here, pointing, if I draw my radial line there, pointing like this. So this is pointing, when I add the two vectors, the net field's pointing like that. And then clockwise here would be pointing perpendicular to this line like this. I'm the same distance away from both charges. So at these 2 points, so at this point, these two vectors, their vertical components, cancel out. And up here, perpendicular to that line and in the clockwise direction is like this. And again, the vertical components cancel out and leave me with something pointing that way. For part C, we have two wires carrying current out of the page. So this would be the opposite of what we have in part B. So you can try and do this one on your own. You can pause the video, and I'm just going to show you the direction of the net magnetic field for this one, but you can work it out the same way we did here, but all the arrows would be going in the opposite direction. So you can pause it now, figure it out on your own. And what you should get here is still 0 in the middle. Here the vector would be going to the left instead of to the right. Here the vector would be going to the right instead of to the left. Here the vector is going up. Here the vector is going down. Here the vector up here, it was going to the left and up. Down here it's going to the right and down, and more to the right than down. And here to the right and up, but more to the right. Okay, and then for part D, we have a current of negative 2I, so that's carrying current into the page, and here we have current coming out of the page, but the current here is only I, so this current is larger than this current, which means that the magnetic field from this, going back to our equation here, since the magnetic field is proportional to the current, the magnetic field from this is going to be twice as large if we are the same distance away. So let's compare this to part A, and the difference here would be instead of a negative I, we have a negative 2I, so the arrows that we have from this wire are going to be twice as large as what we have from this wire here. So the directions are still the same, so in between we had the field from the individual wires going upward, so the net field is going upward, so that's still true. And then over here, from the negative 2I wire, the field would be going straight downward, and that is still going to be the larger one because we're closer to this wire and it has more current. And for this wire here, this distance from here to here is 3 blocks. From here to here is 7 blocks. So we're closer to the wire on the left. The wire on the right has more current, but it would be 0 for the magnetic field if we were twice as far away from this wire as we were from this wire, because the current's twice as much. So if we're twice as far away but the current is twice as much, we'd have the same magnitude for the magnetic field from each wire, so it would be 0, but it's 0 here. So we're a little closer, well, we're a little closer to this wire than we here where it's 0. So the magnetic field from this wire is still larger, and from this wire we get a magnetic field pointing downward. You can compare that to what we have here. So the contribution from this wire is still the larger one because we're closer to it, and at this point that's where the field is 0. And then on the other side of this point it would matter more that this current is twice as large, and then the field would start pointing upward over there. Okay, and then when we go up to this point here, I have a contribution from this wire, which is perpendicular to this line, pointing in this direction, that is in the counterclockwise direction, so that's like this. And from this wire, I'm the same distance away, but this wire has twice as much current, perpendicular to this line and pointing like that, twice as large, gives us something like this for the net field. Okay, then if I go down here, perpendicular to this line, pointing in the counterclockwise direction, whoops, like this, pointing in the counterclockwise direction, that's like this. For this, stick your thumb into the page, that's pointing in the clockwise direction, and perpendicular to the radial line, that's pointing like this, twice as large. So we get something, instead of pointing straight up, it's pointing up and a little bit to the left. And then beneath this wire, the field is pointing this way. No, it's pointing that way. And then we have something perpendicular to this line. Stick your thumb into the page, your fingers are going like this, so that's in the clockwise direction, twice as large as it was over here. And that gives us, when we add these two together, something like this. And we're only concerned here with the general direction, so we won't worry too much about how those individual vectors for the magnetic field from each wire are related. And then when we're directly beneath this wire, stick your finger into the page, the field's going in the clockwise direction perpendicular to the radial line. So that's like this. We have a smaller component from this wire, it's perpendicular to this line. Stick your thumb out of the page, the field's going in the counterclockwise direction, so that's like this. It's a small component, and so we add these two together and we get something pointing like that. The angle that we have here should be larger than the angle that we have here. Okay, so that concludes problem 16. This problem is supposed to give us an idea of how the direction for the magnetic field works. And now that we have this under our belt, we're going to tuck this away for a while and move on now to problems using the Biot-Savart law, because that's going to be coming up in our lab.